Hello everybody and welcome back. If it's your first time here, we are working on an operating system from scratch. Today I want to tackle the body allocator, which will serve as a base for our general purpose heap allocator. So let's get to it. Right, so body allocator. I guess I should go over here and just create a new file. Yeah, sure, let's go body.sig. So for reference here, I have two sources here. So I have the Wikipedia article about body memory allocation, which goes a bit into describing how the algorithm works. And the most important thing here is this example that we'll get back to in a bit. And the second one here, let me just zoom in a bit, is some old kernel documentation that basically refers to kernel version 2.6, I believe, but that describes how the body allocator is used in the kernel to allocate physical pages. And we are going to so basically, I went through this, did some reading to basically have a better understanding of how this should work. But yeah, these are the two sources I've used for this. Right, so let's go back to the Wikipedia article here. So the way the body allocator works is by having, so we have some sort of memory. So in this case, it's this block here. And this block of memory is basically 1 meg in size. And we decide on what is the smallest chunk we'd like to be able to allocate from this body allocator. And here in their example, they have decided that the smallest allocation size should be 64 Ks. So that's what is shown here. We have this full block of memory here, which is the 1 meg block. And we have a view which shows all the 64K blocks that can be allocated within that block. But the question here is, how do we actually allocate any size? And that's what this diagram here shows. If we want to allocate a size of just 64K, we have this block here that's not been split, so it's 1K block. We have to decide to split that, so that's what's been shown here. We split that block into two parts, and since that other block is 512 Ks, we still have ways to go, so we split that in half too. Now we have two blocks in this half block here. Same goes here, all the way until we get to a block that can fit our size. So this one is just 64 Ks, and we allocate that. Now, this block here and this block here are what's called bodies, as well as this block here and this block here. This one and this one, and then this one and this one. And the idea behind the body memory allocator is that once both bodies are free, we merge them together to have this one contiguous larger block. And we repeat the same. If this body is free and this one is free, we merge them up to have this larger block, etc., until we can recombine our full memory we are working with. And the reason behind this is that we want to recombine them as often as possible and as quickly as possible to avoid internal fragmentation, so that we avoid having just one bit of memory being allocated that blocks us from allocating the rest of the memory. So that's the main idea here behind this algorithm. And this is basically what they are showing here. So in step, so from step 2.1 to to 2.4s. We split recursively the blocks until we get the block size we need, which is this one here. We allocate this A allocation here. Then we get a request for a B allocation for what's this? This is 128 128Ks. So we find the first block that has that size. Otherwise, we go ahead and split a larger block. So we already have this block here that was free, so we allocate that. Then we get an allocation for C, which asks for 64K. We take that in here since we already have this 64K block free. And then we get a allocation for D, except that this time here we did not have a 128K block free, so we went ahead and split this one into two chunks, two halves, and then we allocated the left half to this allocation D here. Here we do the reverse. So in step 6, we have freed the B allocation. So this one here is free. And here we have freed the D allocation in 7.1. And in 7.2, we see the effect of the body memory allocation algorithm, which is recombining the two bodies since both of them are free. I'm talking about this body here and this body here. So we recombine both of them into this full block here, so that if we ever need to allocate a what's this supposed to be, 256, I think, Ks, we'd basically have it here instead of having to fragment this other block and create a bunch of internal fragmentation within our allocator. So here in step 8, we free the A allocation. So we have this this body here that's half free. So A and C are half free. In 9.1, we free C. So now this body here can be recombined. So we recombine it to this one here. And this body here can also be recombined. So we recombine it to this one here. Same goes for this one. We recombine it. And then this one and this one gets recombined to our full memory. So we basically wasted no memory here. And yeah, this goes into describing how the memory allocation works. In their example, they go a bit into detail, showing how allocating sizes that are not a round power of 2, because since we are splitting by dividing by 2 each time, and we are starting by having a memory size that's a power of 2. All of the allocations will have standard sizes of power of 2s, except that when we get requested an allocation that's not a power of 2, we have to round it up basically to the nearest power of 2 that can be allocated within our allocator here. Also, there's this notion of order. So order is basically the way I think about it is that order 0 means the smallest block we can request. So here we get requested an allocation for 34K. The smallest block we can allocate is 64K. So that would be a order 0 allocation. If we have no order 0 blocks, then we go ahead and try to split an order 1 block, which would be, so this one would be an order 0, this one would be an order 1. So we try to split this one. If we have no order 1 block available, we split an order 2, etc., until we reach the highest order memory that we can split, which is basically always would be the full size memory. And same goes for freeing the blocks. If we free an order 0 block, then we try to merge both order 0 blocks, so this block that's been freed and its body, to basically have an order 1 block and so on until we basically recombine the full memory if it's totally free. So let's for a second take a look at this document here. They have this diagram which basically shows that they use sort of free lists. So this, I believe, are, yeah, so these are linked lists that basically represent all the free items that are that can be used to allocate within each of the orders. So basically they have the highest order, which is the full memory that we are working with. And for every order above that, we can have the bodies, which are the splits of this full memory here. And here they are using a free list to manage those, as well as a map. And this map here is a bitmap that basically gives us the state of each pair of bodies. And the curious thing here is that they're just using one bit to represent the state of each of the bodies. I think I understand why that is, but we'll see. So, and every time one of the bodies is freed, they check this bitmap here, or the bit representing the two bodies in this bitmap, to see if they should combine or not. And they try to do the recombining of the bodies as soon as possible, because that would basically give a best case scenario for allocations and for reducing internal fragmentation. All right, so that's enough yapperoni for one video. So let's get started. So I want to get started. So I think we are going to need to do some math things, and I want to do. So I have no idea how to structure this as of yet, but we are going to discover along the way. I'm pretty sure this. In theory, this should be easy, but I'm pretty sure it got hands. So let's think about this. Actually, since we want to, so we'd like to have some sort of slice, right? Some U8 slice. Hold on, let me just put this as a comment. So U8 slice, which would be the memory we can allocate, right? We also will need to know what is the smallest allocation size, right? So as an argument, maybe as a comp time argument, we also would like to know. I also would like to implement the allocator. So what's it called? Interface. Right. So these are the things we know to start with. Okay. So let's, since we are taking comp time arguments, actually, comp time config as input. I believe I've seen in the Zig, you can actually check that, Ziglang. I believe in Zig standard library, if we go to some allocator, so fixed, sure. Probably not this one, but if we go to general purpose allocator, yeah, so they do have this, where is it? yeah, so they do take a comp config in their allocators. So we should probably do the same. So public function body, and this here would be a comp config, which is a body config. And this here, of course, would return a type, and this would be return a struct of nothing. And here I'm just going to go ahead and do body config is struct. And for now, I think this struct here would just have, let's think about this for now. Let's call it memory. Yeah, this would be a U8. So we can pass it our memory. And we should have the min size. Let's call it min size. And this would be a U64. Right. So here we are going to need to compute a few things. Since we are going to work with powers of 2, I think, or rather, since we are going to work with divisions by 2, we are going to be working with powers of 2. So I'm going to just take the logarithm of all of the sizes, memory size and min size, just so that we can shift left and right as we see fit for the rest of this. So what should we call this? Min size is min block size log, and this would be std_math log2, I believe. There's a log2, yes. And this would be config.min size, sure, and const. What should we call this? Max, sure, max block size. Block size log is std_math log2 of config.memory.length. Sure. Oh, right. So now we need to know. So here's the thing. In the Linux kernel, they have built this free list that basically has these tiers. And for our example, let me just do this. For our example, I'm just going to go from, let's say I have a memory. My memory is a U8 slice that has a length of 32 bits, right? So this would be 0 to 32 memory. And I want to allocate a minimum size of 8, let's call it bytes, not bits. So 32 bytes, and I want to allocate a minimum size of 8 bytes. So that means that I can, in theory, have, so this one is the full memory, this one is the first split, then this one is the second split. So this one would be 16, this one would be 8, and I wouldn't have this, right? So that means that here I have about, so this wouldn't be order 0, order 1, and order 2. And from 32 and 8, I think if we take so 2 to the 3, which is 8, and 2 to the 5, which is 32, I believe, and we take the difference between these two, we basically get the number of orders that we can have. So how many times we can divide by 2 to get from 32 to 8. And this is basically just 32 divided by 8, which is 2 to the 5 divided by 2 to the 3, which is also equal to 2 to the 5 times 2 to the minus 3. And multiplying is basically adding, so it's 5 minus 3, which is just 2 to the 2. So, and this one here would give us the number of orders we can have. So log of, basically log of this thing here would be the number of orders. So let's do that. So max order, and this would be a no, actually this would just be a constant max order, and this would be the max log size log minus min log size log, I believe. Right. Now, now that we have this, we are going to create a free list, or rather an array of free lists. So free lists, or let's call them allocation buckets, just buckets, I guess. So buckets would be a max order. So we have max order buckets of some body bucket item. Not sure how to put this, but bucket free list. Let's call this the bucket free list. That also means that I'm going to need to import doubly linked list, which is I think in list.sig, correct, and there we have it. And that also means that we can, it doesn't need to be public. We can go ahead and define a bucket free list as a doubly linked list of some type, which I'll call, what should I call it? Bucket item, sure. Prev and next. All right, so here we should also have a bucket item, which would be a struct that basically has, what should it have? Well, it should have a priv, it should be an optional pointer to self, or sure, let's annotate it like so. Next, which would be the same pretty much. This, and it'll have, let's think about what we want to have here. We'd like to have the address or the node ID. So let's think about this. Let's imagine we have, this is the state of our allocation here. So this is order 0, and this is order 1, for example. I'm just basing this on the same example of 32 bytes with 8 bytes of min allocation. So what I'd like to have in this item here is to tell me which of these, which of these cells is the first free cell for any of the allocation sizes. So this one would be 8 bytes. So if this one is allocated and this one is allocated, I want this, I want the first item on the free list to be this one here, basically. And if this item here, this list does not have any items left, this should indicate to me that I need to go up a level, split this, allocate this, and put this into the free list. So that's the idea here. So let's for now call it node index, and let's type this as node index for now. I'm not sure. I'm not sure how this will go, but for now, let's just type it as that. Let's also go ahead and create this within this. And let's do const node index, which would be just an integer. And this would be math int fit in range. So what is our range? Well, basically it starts from 0, I guess, and it goes all the way up to, well, I guess it goes all the way to, so 1 shifted by, right, okay, so maybe I should extract these to here. That might be a good idea. So this one would be max block size minus min block size. So basically the node index can be from, if I just go back to my example, this is level 2, level 1, and level, or rather order instead of level, but you get it. So this one is order 0, 1, and 2. And this node index here can have a maximum of this number of cells, because here we have half of those, and here we have half of whatever is here. Or rather, in the topmost level, we should have exactly 1 cell. So that means that this node index here can be at most the number of items in this 0th order level. And the number of these items is basically the memory size, which here would be 32 divided by 8, right? And this would be 4, which is the correct number. And another way to see this is basically 2 to the power of 5 minus 3, which are the 2 logs we have here. So that's what we are doing here. This is 1 shifted left by the difference of those 2 logs. So that should give us the total number that we get here. Right. So, and actually, I think we are going to do quite a few binary tricks in here, because we are working in powers of 2, so that should be fun. Right, so now we have our buckets. We should also have, if I go back just 1 second to this, I'm not sure how we are going to use it yet, but I'm going to create this bitmap, and let's create it first and then think about it. So let's call it node state. Yeah, not a huge fan, but okay. So this would be stud. I believe there is a static bit set, sure. And this one here would have a, right, let's think about this, since I need to figure out the size. Let's think about how this should be. Right, so let me put here the same example from before. This is our second order, this is our first order, and this is our 0th order. So every cell here would have 3 states. And by the way, this basically forms some sort of, this is a binary tree basically. So let's think about this for a bit. Every cell would be either untouched, so unused, let's call it, unused, or it will be split, or it would be used. And let's see if this covers all the states. So let's imagine that this case, this cell here is allocated. So this one here would have, this would be used since we have allocated it. Its parent here would need to be marked as split, right? Since it's split, and it still has one child that's not used, so it still has one free child. This one here would be, let's replace unused by free. So this one here would be free, right? This one would be free, and this one would be split. Right, now let's assume that both of these cells here are used, so all of them are marked as used. This here goes from, it goes to used, since all of its children are used. And this one here, does this one remain split? I think this one should go to be used at this point. Yeah, since all of its children are. So I guess free means all children are free, are unused. Split means that at least one child is free, and use means that all children are used, basically, are allocated. And I think this order here, this order 0, does not really give us any information that we don't already know. Let's think about this. So the fact that this one is used, we already know because it's not in our free list, and we don't have to deal with it. So we don't really care about knowing how this is used. If we try to free this cell here that's already allocated, we are going to need information about its sibling, its buddy. We want to know if its buddy is free or not. And we want to know if its buddy is free or not without having to look up its buddy. So if this one is split and we are getting freed, that means that we were used. So we can implicit this state here without having to store it. And if this one is split and we are used, that means that our buddy is free. Because split means at least one child is free. And since we only have 2 children, that means one child is used and the other one is free. So split here would be basically so it would be child 1 XOR child 2, I believe. So it will be set to 1 if and only if one child is free and the other one is used. Right. So if we go to this case here where both children are used and we want to free this child here, this cell here, this parent, will have its state set to 0. So it's not split, it's used, basically. And since this one we are trying to free it, we already know the state of this one, it's used. And that means that because this one is 0, it's not set as split, we should be able to intuit that the child, the other child, the sibling, is used. And then here we'd have to set it to 1 since we have freed this one, and this cell here, this parent, transitions from being used to being just split since it has one free child. Okay, so I think we can get rid of all states here. And I believe that's what they did here in the kernel by using just 1 bit to save the state of a pair of buddies instead of having just to basically describe 3 states, which would require 2 bits. Right, okay, so now that we know that, how big is the bit set? So let's do some math. So we want to have all levels except the last one, because the last one can basically be intuited from its parent. So we want 1 bit per cell, possible cell here, except for the last level. So how many cells do we have in total in these 2 levels? So from this here we have order 2, order 1, and order 0. And if we just go ahead and write that, so that would be 2 of basically order 2 minus 2 plus 2 of order 2 minus 1, which is this here from max orders. And that's pretty much it. And that would give us basically 3 nodes. Otherwise, if we want to have the number of all of the cells that we have, it's basically the same thing as with binary trees. So that would be 2 to the power of the height of the tree and minus 1. So that means that here, for us, if we compute basically all the nodes in our tree here, the height would be 2. So that would rather 3 levels. So that would be 2 to the 3. So that's 8 minus 1. So 7 nodes, and that's correct. But we want to ignore the last order here. So it's inconsequential for our I guess algorithm. So this one would be 2 of height minus 1, or rather, if we have to rewrite this with things we know, this would be 2 of 2 to the power of the max. Is this it? I think this is it. 2 to the max block size log minus 1. So call it block size minus 1. And this would give us 2 to the 2, so 4 minus 1, so 3 bits needed. Right, so let's put that in. Let's call that 1 to the max order, I believe, minus 1, minus 1. Sorry. I think that's pretty much it. Okay, cool. Right, so now let's do something first. Let's create function, or it should be public function allocate. And this allocate here would take, well, first of all, self, which would be a pointer to self, which we haven't yet created. Yeah, sure. So const self is this. Yeah, sure. Okay, and it will take a length, which should be a U64. And I think we are going to try to return a slice of our memory. And this would make it easier to adapt to the allocator interface. Yeah. Okay, yeah, so sure. This would be that. And I guess we have forgotten about something. And what is that thing? I guess we should also take memory to be config.memory. Sure. Yeah, sure. That should be fine. Okay. And let's also take so min block size log to be min block size log, and max block size log to be max block size log, just so that we can look at them if we want to debug. And actually, this one is actually not good. So we need a type here instead of whatever this is, and this would be so U64. So here I'm tempted to add, so okay, let's not get too involved for now. Let's just write down a to-do, add debug info, and allocation tracking. We'll see how easy or difficult that is when we get there. But basically, these two things here, we only need for debug, so we could make them zero-sized in release builds if we so choose to do. But for now, let's just keep going. Right, so this one here, I'm pretty sure I'm going to need to initialize this to something. Yeah, so this one here would be something like this. Rather, it should be bucket free list of. Actually, let me just do this here to make life easier for myself. Node index, yeah, sure. So here would be so head. I guess list already initializes to null. Yep. So that's fine. So we should just do max order, like so. Cool. So now we have our array of free lists initialized. We need to, before we do our allocation, we need our init function here, which basically would return a self. And this would return we would like to have our order. So for some reason, the Linux kernel and the Wikipedia article uses order 0 for the lowest, or rather more split allocation buckets. And that means that if we want to initialize our free list here, we need to put our full memory block, this memory here, into our highest order item. So that means that we should do something like what should we do? Let's do var body is this, and of course we need to give it a type, so self, and then we need to do body dot buckets at some order, so max order -1, and this would, we need to append to that. So we need to append to that a node, and we are going to need to allocate nodes. So okay, so that needs to come out. So allocator is the mem allocator, I believe. Sure, not forgetting anything, I believe. So let's create a const. First node would be alloc dot create. create, and it needs a type. Type would be bucket bucket item, and this here would need to be first node. Right. So we also need to do first node dot that is of course we need to try that, and this can actually fail, and that means that this here would need to be node index of 0. Yeah, sure. Node index of 0, and then we put that into this. This bit set here would need to also initialize. I believe we do have a few. So init empty, I guess, is what we are looking for. Init empty. Actually, let me just do something like, since we already know that we are going to have a fairly large bit set, I'm going to use array bit set directly instead of just using static. So array bit set, and I believe that's in something like is there no bit set thing? Yeah, there we go. So this should have so init empty, and that looks okay. So does that resolve? It does. Cool. So now we have initialized our struct, and we have a fairly okay-ish idea of where we want to go. So let's try to go there. Right, so the allocation process, the algorithm for it, would be fairly straightforward in theory. So first of all, I'm going to need to find, let's call this requested length. Let's call this length, and this would be setMath dot is it math or is it mem forward align forward? So we want this to be a let's think, a U64 is the type. The address, or rather the requested length, would be this one here, and the element would be our min block size. Log is there? Log2, yes. Log2 alignment, and that means that we don't need that. Just going to need to go into here and see where we. So it takes U size. I'm not really the biggest fan of working with U sizes. Yeah, I'd rather just force this to be 64. What's the problem? Requested length. Okay. And I guess it's not happy about this, so let's do something like that. And now I guess we can get rid of this. And let's keep on going. So now we have our length. We are going to need to basically get where our matching bucket. So where is the bucket that matches the size of our length is the thing here. So this would be, let's call this length to bucket index. And And should I also create a bucket index here? So this would be student math int fit in range goes from 0 to max order, except that max order is defined within this max order. I guess max order -1 would be better. Yeah, right. So this one here would take length, and it should, in theory, give us our so length to bucket index takes a length of u64 and returns a bucket index. Right. So how do we go about this? So we have our, let's bring out the pen again. So I think if we just take our length and divide it by the minimum allocation size we can have and round that up, we should have so I guess there's a log2 that needs to be taken there, but we should have the order we need to be in. But that means that we need to add logic to basically cap it so that it does not exceed the maximum amount of memory allowed, and cap it so that it doesn't go under the minimum log size. Now, I guess the minimum log size is not really a problem since we've aligned forward by that alignment. But I think I'm going to go the easier route here by just doing so const let's call it var order would be max order -1 and var size would be the minimum size. So it would be, I guess we don't have that. So min size is u64, which is config dot min size. Right, so self dot min size, and I guess this one here takes self as a const pointer, and I guess we can do while size is less than length. Yeah, sure. We can do so size. So we need to, I guess, double the size, and order would be decremented by 1. Yep. Okay. And then here we should return the order. And now I'm thinking about renaming bucket index to order index, but for now let's leave it be. Okay. So this one here would be matching bucket. So now that we have our matching bucket, we need to go to our free lists and see if we have anything in our free lists. So const node is our so self.buckets at matching bucket, right? And we want to pop first. Okay. And if we have a node, so if node, so let's rename this maybe node. If maybe node, I'll catch that as node. We need to do something with it. So I guess this would self.alloc.destroy destroy node. And I guess I haven't put alloc into self. Cool. So alloc would be allocator, and that means that in it's somewhere here. I'm going to need to pass it alloc to be alloc. Right. So now we have self.alloc. So what we did here is we've popped our first node. We found a free node from the list. We destroy the node, but before we do that, I'm going to take the node index. Sure, is node index. Right. I'm just going to need to check that this here returns null. If it finds nothing, that's correct. Right. So now that we have our node index, we are going to need to basically get the pointer from our node index. So pointer from node index, and I think this here we've forgotten to put a self dot, so that should help. Right. So pointer from node index. Let's take care of that. Pointer from node index. That should take a node index, which is a node index, and it should return a U64. Yeah, sure. Right. So what should we do here? Oh, we also need, because we have, so basically let's redraw our example here. This would be this, this would be this. So this node index 0 would basically refer to any of these three cells or nodes in our tree here. And the only way we can differentiate between them is by having the order ID or the bucket index. So we need to also here take a bucket index, should be a bucket index, and that's the only way we can actually differentiate between those items. Right. So now that we have our bucket index, how do we compute our pointer from the node? And I guess we should also think about having the node index from pointer. So this would need bucket index and a pointer, which would be U64, and this should return a node index. Right, so let's start by, I think this one should be simple. So let's redraw. We have our memory, and our memory is split to some order. This address here is our basically memory.pointer. So let's call it start, str, t. So we don't confuse that with something else. And we should have some index I. And the way we can find the pointer from, so we want this pointer here from this index here, is by, and of course we have our bucket index. So we need to get our bucket index, figure out how many splits we have in this bucket index, and then do start, our pointer would be start plus the node index times the size of each split. Yeah. So now let's figure out, we need to figure out this, which is the size of each split. And the size of each split would be basically the memory, the size of this memory. So let's call it memory size divided by the number of splits. So divided by n, and this n here would be basically the number of nodes in the level given by the bucket index. So that should be, so in order 0, which would be the lowest order in our example, that would be 2 of 2 minus 0. 2 being max order, and 0 being the current order. And in order max order, we should have one split, which is just the full memory. So that's let's check that. So that's 2 minus 2 is 0, 2 to the 0 is 1, right? That's correct. So that this n here would just be 2 of max order minus the current order, which is bucket index. And we divide the memory size by that. And if we do this in just log2 len, so that we can make all of this easier, we already have our max block size log, which is the log of our memory size. We should have just max block size log minus, so this max order plus bucket index. And we should, this should give us the size, and then we should just take that, multiply it by the node index. And I guess we should do something like this, multiplied by the node index, and we add the start pointer to that to give us our pointer. Yeah, so that's for the pointer. And I guess for the node, that would be the reverse. So we have our pointer and we want to the node, so that's p minus s over length is n. And of course, this would require some rounding to be done. So I think we are going to, no, let's round it using some other method. Right, so pointer, const pointer would be, so self, and I guess we need self here. This would be a const to self. Pretty much the same should be done, whoops, here. So self.memory dot start dot pointer, rather. And let's call this, actually, let's do this. Let's call this start pointer. And here we would like to know the nodes. So const node length. And this would be, so we need to know how many nodes there are. Or rather, node length would be just one of, so one shifted left by what we've seen earlier. So max block size thingy minus max order minus 1. Yeah, max order minus 1. And to that we add the bucket index. Yeah. I'm pretty sure there are a few things to be done here, so let's try to do this correctly. This should be cast to U64 just so we can avoid any issues. So now that we have our node length, we should pretty much return start pointer plus, and I guess here we need to do int from pointer, right? And let's get that as a U64, actually. So start pointer plus node length times node ID, node index. Right, so that's for the pointer. Now let's get the node from some sort of pointer. Let's get const, let's call this offset. Yeah. Actually, let's make this symmetrical. So let's call this const offset, and this would be node length times node index, and this here would be offset. So pointer start plus offset. So this one offset would be pointer minus self.memory as U64 int from pointer of self.memory.pointer. So that's the offset. Now we have the offset. We can go ahead and do node index. That would be offset shifted right by max block size log. And we need to remove, I guess, let's do this of bucket index. So we are not sure that this pointer here is aligned to the same alignment that we need for this division here to be exact. So I'm guessing that we are going to need to align it forward. And we are going to do that by adding so one size of the bucket. I think we should be doing this. Right, and here we are just going to return node index. Right, and here we're just going to do as node index. We should be having quite a few things to fix when we try to compile this, but let's try to do our best. Actually, now that I think about this, I think the alignment should not be done here. So here I'm going to need to write some tests for this and the function above to make sure that it behaves nicely in all cases. But for now, let's move. So now that we have our pointer here, we should basically be returning a slice, or rather, let's first of all, before we do that, let's do so how should we call this? Let's call it slice. And this slice here would be so as a mini item pointer to U8. So pointer from int of pointer. Right, and this should be slice of 0 to whatever length we have been requested. Right, so that should do it for this case here. Now we have the other case, which is, well, fairly interesting to say the least. So in this case here, we haven't found a node for our matching bucket. So we are going to, I guess, need to iterate on buckets. We need to iterate on buckets going down, because our zeroth bucket, zeroth order bucket would be the one with the finest allocation. So we need to go down from matching bucket. So matching bucket plus 1, I guess, would be our start. So while bucket is less than max order, so let's think about this for a bit. So if we have anything on this bucket, we basically need to repeat the same logic here. Yeah. So we are going to need to repeat the same logic. So is there a way we can rewrite this without having to do a bunch of copy pasta? So let's do var bucket is matching bucket, sure, and let's put all of this in a while loop. Let's think about this. Max bucket, max order. We should always be doing the search downwards. Yep, that looks okay. Now we need to do this. Basically, that needs that. So if we go for our first bucket, which is our matching bucket, if we do find our node, then that's fine. Otherwise, we should be just go into the next bucket. So bucket would be plus equal 1 and continue. But before we continue, we are going to need something. So in this case here, if we found a node, if our current bucket is larger than our matching bucket, that means that we are in so this should always be done. So if our current bucket is larger than our matching bucket, we should be splitting our node. Right. So to split our node, we are going to basically we need to insert in bucket -1. Yeah. Okay. So that should be it. So const new have node. Yep. So this should be self.alloc.create a bucket item. Sure. And have node. Let's initialize that to be. So we only need to put in node index, I believe. And node index here should be, so whatever the node index of our parent is, so let's move this up here. This should be node index +1, I believe. Because if we are splitting this into its two children, we will take the left child to be allocated. So the one that needs to be pushed onto the free list would be the right child. And the right child is always left child +1. And I'm doing this by assuming that the children IDs are, or rather the children are laid out in quote unquote heap style layout. So we have sibling 1, sibling 2, and then we have the children of this first node here, this one and this one, and then we'll have the two children of this node here, and then this one would have its four children, or rather its two children here. This one would have its two children here, etc. So to go from a node ID to its first child, we multiply by 2, right? And if we want the right child, we multiply by 2 and add 1. Next. That's it. Right, so now that we have that, we need to insert that half node into our self bucket or buckets at bucket -1. Yeah, bucket -1 append, or let's try to think about this. Should we append this or prepend this? I think we should always prepend. Let me just think about this. Yeah, let's prepend this for now, and we'll see where we go from there. Okay, so that's that. And if we did not find it, then we bucket +1 and continue the check to our other bucket. But that means that this one here would need to be done recursively until we do find a yeah, this is not as easy as this. So if the bucket is larger than our matching bucket, we should, or rather this should be a while loop. And this should be bucket minus equals 1. Yeah. The reason for that is if we skip a level, if for example we have just this order 2 here, and so let me annotate this is the free list. So this is the list, and this one is empty, and this one is empty. If we try to allocate something here, this one is empty, so maybe node would be null. We go to the else. Bucket is +1, so this one is 0. We go to 1. We try to pop first. This one is also null. So we go to bucket +1, so we arrive here. Then we do a pop first. We get this whole block of memory here. Its node index would be 0. And what we are going to need to do is, while this bucket here is larger than the bucket we wanted to allocate, we are going to need to just split this in halves, and then, or rather, hold on. We insert this one, which would be this half here, and then this half would need to go here, and we insert its right child, which would be this one here. Yeah. So while this bucket is larger than our matching bucket, we need to recursively create these buckets here. So we want this to be created, and this one would have an index of 0 + 1, which is 1 here, node index. This one here would have 0 + 1 also, which is node index 1. That should be fine. And we should, yeah, that looks pretty okay. And at the end, we found our pointer, which is our node index. So this one's node index is pretty much its parent's node index. But we need to apply this transformation here. Right. So I guess we need to do that. Before we move, we need to do node index is equal to node index times 2, since we are always taking the left child. Actually, let's do something like where is our node index? So let's change this to become so const node index is a struct that basically has a value, which is whatever we've put here, basically. And we'll have a public function called parent, like self, and just this, and returns a returns something like this, and I'll just paste this to be left and right. Left child. No, actually, let me just do something like this. Sibling. So this one here would take that, and it would take let's call it side, and this would be an enum that has left and right. Sure. Okay. So this one would need to return. So value would be self.value divided by it would be value minus 1 divided by 2. So let's do something like so, and do something like like so. This one here would need to return something like this, and this one would be value, and this one would have a let's switch on side, and we need to do left. This would be self.value times 2, something like this, and right would be self.value that's an oopsie, plus 1. I guess this should be okay. That should do it. That should do it. And then sibling here would need to return. So here we need to be a bit smart about how we do things. Because I think we can compute if we are the left or the right sibling just by looking at if we are an odd or an even number, or rather the value is an odd or even number. And in that case, we should just actually if assuming that this one is the representation of value in binary, we only care about the very last bit. If it's a 1, we want to set it to be 0 to get the sibling, and if it's a 0, we want to set it to be a 1. So I guess we just need to XOR it with 1. Sure. So this one would be value would be self.value x or 1. We'll need to test this, but for now, let's just roll with the punches. Cool. So here we need to get node index dot child left. So for some reason this is not so this, let's just note that this is a node index. And this should work, right? Otherwise, this here would need to be node index.child right. Cool. Right, so now we have managed to do the actual allocation, but we are still missing a crucial ingredient of all of this, and that is we are not tracking the states of our items. So this node state here, this bit set, is still untouched. So we are going to need to do something about that, aren't we? And how are we going to approach that? So where do we need to make changes? I think this here would need to have so every time we split a node, we should go ahead and mark its parent as split. Yeah. So here we have our bucket. We should mark its parent as split. So let's do self dot node state, I guess, set, and we need to pass it an index, and that index would need to be a node index dot parent. Actually, we need to toggle it, because toggling it would be the same as doing the XOR for which child is set or not. Right, so we toggle those parents. And I guess we still need to do one more toggle here for the matching bucket itself. So self.node state dot toggle so node index dot parent. Yeah. That looks okay. So we are going to need to unit test this, but for now it looks pretty okay. Well, that's all I have time for today. This is a good point to break this implementation here. We've covered quite a bit of the theory behind the body allocator, and I think we've discovered pretty much all the main points and things that we need to pay attention to going forward. So we are going to complete this next time. As always, if you've liked this type of content, hit like, subscribe, leave a comment down below if you have any questions or remarks, and until next time, I'll see you. Fucking out.